Bismillahirrahmanirrahim. Gauss's law, electromagnetic field theory. The statement of the Gauss's law is that the flux of the electric field out of an arbitrary closed surface is equal to the electric charge enclosed by that surface. So consider a spherical. It's not a cylindrical. Spherical. We can take any of the closed surface. We can take cylindrical or the spherical or the cube shape or any closed surface. So the charge enclosed by that surface will be equal to the electric flux lines coming out of that closed surface. So as we know that for that spherical closed surface, the flux is always directed towards the radius of that closed surface. So Q divided by 4 pi epsilon r in the direction of the radius. Okay, now we have to prove that uh, flux lines is equal to the charge enclosed by that surface. So according to this formula, we have taken the small surface ds. Okay, so through that small surface the flux lines is also small, that is d psi is equal to d dot ds. Okay, so d, from that we have, this is d, and the ds for in the direction of er is r square sine theta d phi. Okay, so taking the dot product of these two we will get this. Now we have to consider the whole surface. Okay, so we have to apply the integration with the limits of the complete sphere. So the limits for the complete sphere are theta from 0 to pi and phi from 0 to 2 pi. Okay, so psi is equal to d dot ds. This is d dot ds. So taking the integration we will get q divided by 4 pi into 4 pi 4 pi will be cancelled out, so we'll get psi is equal to q enclosed. Okay, so as we have already studied this formula in the previous lecture, that psi is equal to d dot ds in closed loop integration. Okay, so that is also equal to q enclosed. So that is the proof of the Gauss's law. Now we have to find the electric flux density. Okay, so d is equal to epsilon naught e. So replacing the electric flux density in the above integral, so we'll get replacing d by epsilon naught e, taking epsilon naught out of that integration, so we will get e dot ds. Psi is equal to epsilon naught integration e dot ds, that is also equal to q. So dividing both sides by epsilon naught we will get q over epsilon naught is equal to this. This is the equation in term of e and this is the equation in term of d. Okay, now if we have this is the small this is a point charge. Now if we have a volume charges, so according to the volume charge density, rho v, q is equal to rho v dv. So as we have already proved this equation, so d dot ds is equal to q and q is also equal to rho v dv. So which means these two are all also equals. By comparing these two equation we will get d dot ds is equal to rho v dv is equal to q. Okay, so all these three are equal. Now applying the a divergence theorem. According to divergence theorem, psi is equal to d dot ds is equal to divergence of d. So comparing this with this equation, so we will get rho v dv is equal to uh, del dot d, means the divergence of d. Okay, so the integration will be cancelled out by taking the derivative on both sides of the equation. Okay, so we will get rho v is equal to a divergence of d. Del dot d is equal to, this is also known as the Maxwell first equation. This is the Maxwell first equation in term of d. Now the Maxwell first equation in term of e, replacing d is equal to epsilon naught e. So uh, replacing d by epsilon naught e, we will get a divergence epsilon naught E is equal to uh, rho V. Okay, so epsilon naught del dot E is equal to rho V, or del dot E is equal to rho V over epsilon naught. Now, switching to the application of the Gauss's law, the first application of the Gauss's law is the line charges. Okay, so we have a cylinder that is full of charges, uh, limiting from the 0 to L in the direction of Z. Okay, and as we know that the D is always directed towards the radius, so this is in the direction of arrow. Now, E in the direction of arrow, similarly D is also in the direction of arrow. So applying the Gauss's law, D dot ds is equal to q enclosed. So this is the closed loop integration. So it means we have to take all this, we have to consider all the surfaces. So for the cylinder we have three surfaces. The one is this cylindrical surface, that is the curvy surface. The other is the top, and the last one is the bottom. Okay, so the curvy surface is in the direction of rho, the top is in the direction of z, and the bottom is in the direction of minus z. So we will find these integration one by one, and then at the end we will add up. Okay, so let's have a start from this cylindrical surface. So ds is equal to rho d phi dz in the direction of arrow. Now d dot ds, taking the dot product of d and ds, so we will get d rho d phi dz. Okay, this is this differential surface in the direction of arrow. Now uh, psi is equal to d dot ds, so this is the dot product of these two. Now considering the full uh, limits, full cylinder, so z, and the limits for the z are uh, from 0 to L, and the phi from 0 to 2 pi. So applying the limits, applying the integration, we will get d rho 2 pi L. Now uh, the top surface, which is in the direction of az, as d is in the direction of arrow, and as ds differential surface of the top of the cylinder is in the direction of az. So by applying the dot product we will get 0, because arrow, the dot product of arrow and az is equal to 0, because they are at 90 degree to each other. So psi will be equal to 0 in the direction of z. Now the same case with the bottom surface, because the only difference is minus z. So by applying the dot product we will get the same result, that is equal to 0. So then we have to add these three, d d rho 2 pi l plus 0 plus 0. This is the curvy surface psi, this is the top and bottom. Okay, so we will get this d is equal to rho l over 2 pi rho in the direction of arrow. Okay, and the same, if we want to have equation in term of e, so we will just divide the epsilon naught with this whole equation. So we will get rho l over 2 pi epsilon naught. Only epsilon naught has been introduced in the denominator. The rest of the variables are the same. Okay, now the second application is the coaxial cable. What is coaxial cable? It have actually two conductors. The one is inner conductor, the other is the outer conductor. Both these conductors have their own insulation. This insulation between these two, and this insulation between these two. Okay, so uh, the charges are always appeared on the outer surface of the inner conductor. Okay, plus, and the negative charges are appear on the outer surface of the outer conductor. Okay, so we have to consider different point of observation, means we have to take we have to consider the test charge on different points, and we will find the psi and the d. Okay, uh, psi value, the flux value, so that we we should know that we should know that what is the condition of the flux at different points of the cable. Okay, so um, we have to apply the Gaussian, so we have to apply the Gauss's law. Okay, ds is equal to a d phi dz. Okay, now what is a? A is actually the, okay, a is the radius of the inner conductor, and b is the radius of the outer conductor. Okay, and the point of observation will have the radius of rho. Rho will be the radius of the point of observation. Okay, so instead of radius for the inner conductor we will use a, and for the outer conductor we will use b. So now we are considering the inner conductor, so instead of the rho we will use a. Okay, a is the radius of the inner conductor and b is the radius of the outer conductor. Okay, and we will use a rho s, means surface charge density for the inner conductor. So in means inner, and ou to out will be used for the outer conductor. So applying q is equal to rho s n, and this is the differential surface a d phi dz. The same thing, but the only difference is the variables. Instead of rho we will use a, and instead of rho s we will use rho s n. Okay, now the surface charge density of the inner conductor is given by q is equal to this. Applying the limits, uh, the full limits 0 to 2 pi and 0 to l, we will get this. Okay, so now we have to consider the different the point of observation at different points. For example, first we will consider rho in between a and b. For example, this is the coaxial cable, and this is the inner conductor, and that one is the outer conductor. Okay, this is the outer conductor, this is a, and this is b. Okay, so now where is our row? Our row is somewhere here because it is greater than a and less than b. So the first case is a is less than rho is less than b. Okay, now applying the Gauss's law we will have rho as in which we have found here. So now we have three surfaces for the cylinder. The same uh, the same procedure as we have already done in the previous topic. So we have to consider one by one surface. The first one is the cylindrical. The rest of the two will have the zero answer because the d is in the direction of arrow and ds is in the direction of az. So the dot product of a row in az is always equal to 0. Similar the case with this, we will get 0 from them. So the only non-zero answer for this will be obtained from cylindrical surface. So d, this is d, okay, and this is ds in the direction of arrow. So after taking the dot product, we will get this. The for the top circular surface and for the bottom we will get the zero answer, as I have already told you that because of the dot product of az and arrow, these two have the 90 degree and the cos 90 is equal to 0. Okay, now adding we will get d rho 2 pi l. Now comparing equation number a, this is equation number a, okay, this one, and equation number b, we will get d rho 2 pi l is equal to rho s for the inner conductor 2 pi al. So the 2 pi will be cancelled out with this 2 pi l will be cancelled out with l. So we will get d is equal to rho s in a divided by the rho, okay, in the direction of arrow. Now the same procedure if you are interested in finding the e, so just dividing this whole term by epsilon naught. Okay, this is E in term of rho L. Okay, Q divided by L is equal to rho L. So replacing Q by L by rho L. Okay, so we will get rho L over 2 pi epsilon rho. Okay, now according to the electrostatic phenomena, the positive charges on the outer surface of the inner conductor induces an equal but opposite charge on the inner surface of the outer conductor. Okay, due to the electrostatic induction, uh, as we have positive charges on the outer surface of the inner conductor. Okay, this will induce, just like the phenomena in the capacitor, the one plate is charged by the battery and the other plate is having the charge by the induction process. So now we will have the negative charges, the opposite charges, equal and opposite charges on the inner surface of the outer conductor. Okay, so Q outer will be equal to minus Q inner, same in magnitude but opposite in the direction. The one is positive, the other will be negative. So S rho out, now the outer, okay, 2 pi B BL, because the radius for the outer conductor is B. The same equation, but the only difference is this minus because of the opposite charge, and the other difference is N here is out, and B and the radius of the outer conductor, A is the radius of the inner conductor. So L 2 pi will be cancelled out. We will left with only rho S out is equal to minus rho S in A divided by B. Now the second case is we have to take rho is greater than B, means the point of observation is somewhere here. Okay, now the rho is greater than B. So what actually will happen? To apply the Gauss's law, we consider a Gaussian surface in the form of a cylinder. Okay, this is the Gaussian surface. Gaussian surface means any closed surface. Okay, in which obey the Gauss's law. Okay, so this is called the Gaussian surface. So d dot ds is equal to q enclosed. Now q enclosed, we have two charges enclosed in that area. Okay, so positive and Q negative. As I have already told you that both of these charges are equal in magnitude but opposite in direction. So the net Q enclosed in the whole surface, there will be Q plus plus Q minus. So the answer will be 0, because these two charges are equal and opposite. So the d dot d will be equal to 0. Similarly, d is equal to 0, e is equal to 0. Now the third and the final cases, we have to consider the point of observation somewhere inside the inner conductor, somewhere here. Okay, so rho will be less than a. Okay, so the point of observation lies inside the inner conductor. As the point of observation is located inside the inner conductor, hence no charge is enclosed by the Gaussian surface. Okay, if we have considered a Gaussian surface around the point of observation, means for example, okay, the Gaussian surface for this will be uh, somewhere like this. Okay, now the Gaussian surface will be like this. So no charges will be enclosed uh, around this point of observation or the test charge. So according to the Gauss's law, the psi will be equal to the total number of charges enclosed. Okay, so as we have no enclosed charges in the Gaussian surface, so means q psi will be equal to 0. So as psi is equal to 0, q enclosed is equal to 0, d is equal to 0, and e is equal to 0. Okay. So what we have concluded, we have concluded that the electric field intensity is confined in the medium between the two conductors. This is known as guided medium. Okay. So we have concluded that the electric flux density or the electric field intensity lies only in this region, the medium between the two conductors. Okay, and we have proved that no electric flux or electric field intensity lies inside the inner conductor or outside the outer conductor. Okay, so only confined in this region. Okay, now we have the example, and we will explain this example in the next video. Thank you.